Hi, and welcome to this short clip having a look at the oxidation number of carbon in its common oxides, CO2 and carbon monoxide. This means we have to deal with multiple bonds and also dative covalent bonds when you're deciding how many electrons an atom has involved in the bonding. So let's just take a quick moment to recap on what oxidation number means. It refers to the number of outer shell electrons an atom involves in bonding in a compound. So therefore, it must mean it's bonding to another element. So if we look at oxygen, you can see that clearly the oxygen atoms have involved 2 electrons each in bonding, but the bond is to the same element, so this doesn't count. So the oxidation number remains as 0. So just let's remind ourselves with a little bit of the oxidation number rules. Just focusing on oxygen because that's the one we're interested in. It takes a negative oxidation number as it's electronegative compared to all other elements except for fluorine. Now there's exceptions to that. When fluorine is in a compound, it's always -1. So I'm not going to go down the route of explaining the oxidation numbers, but we're focusing just on carbon oxides, if that's okay. So, coming back to our meaning of oxidation number, we now have carbon dioxide in dot cross form. So dot cross diagrams are a really good way of working out oxidation number. The two skills are really strongly connected. So what I'd like you to do is pause the clip and see if you can predict the oxidation numbers of carbon and oxygen in carbon dioxide. Okay, so I'm assuming you've had a go at that. Let's have a look. So the right-hand side oxygen atom has involved 2 of its electrons in bonding. So has the left-hand side one. If we take the X's, which represent carbon electrons, you can see that carbon is only 1 atom in the middle, and it's involved 4 of its electrons in bonding. So that must mean that carbon has an oxidation number of +4, and oxygen has an oxidation number of -2. So how does this work in terms of adding the oxidation numbers up? So we need to do a quick check. If it's a neutral compound like carbon dioxide, you have to have 0 as the overall oxidation number. So if you take 2 times -2 from the oxygens, that gives you -4 mathematically in total. At the same time, the middle carbon, it's only 1 atom of carbon, that has +4. So +4 and -4 obviously make 0. So let's have a look at it for carbon monoxide. So what I provided as a bit of a hint is a sort of a diagram showing not just the fact it's a triple bond, but also the fact that one of the bonds in the triple bond is dative covalent. So this throws up another conundrum, which we'll talk about in a second. So let's pause the clip again and see if you can do the dot cross diagram like before. Okay, so I'm assuming you're coming back to the clip now, and you allow plenty of overlap between your 2 shells. As you know, it'll be a triple bond, so therefore they'll need to fit 6 electrons in there. The next thing to do is to have a look at identifying which circle is which element. It doesn't matter which way around you do it. So I'm going to match the diagram that I put up at the top and put a C on the left and an O on the right. So we need to think about how many outer shell electrons each atom is bringing to the situation. So group 4 is carbon, so that has 4 electrons in total. Oxygen is group 6, so it'll have 6 electrons in total. So when you construct the dative covalent bond's influence, you have to think about the direction of donation. Is it donating from the oxygen to the carbon or from the carbon to the oxygen? Now you might argue that oxygen is more electronegative than carbon, which is true, so surely oxygen would try and force carbon to donate 2 electrons to it. The only problem is that carbon's only got 4 electrons, whereas oxygen has more, it's got 6 available. So therefore oxygen has to do the donating. So here's how it will work. You have your 2 electrons from oxygen to represent your dative covalent bond, and then the other 2 bonds in the triple bond are the normal type of covalent bond, where each atom puts 1 electron into the bond that it shares. So now what we have to do is populate the outer shells with the remaining electrons. Obviously, they have to add up to 8. So the oxygen gets a lone pair, and the carbon gets a lone pair. But what about the oxidation number? See if you can predict the oxidation numbers like we did before. Pause the clip again, grab a bit of paper and have a go. Okay, so again, I'm assuming you've stopped the clip and are coming back to it now. So actually what happens is this. Now it might not have been immediately what you came up with. So let's have a try and explain what's going on. If you look at the oxygen, it's actually involving 4 electrons in that triple bond. So how come it's not -4? Well, as carbon monoxide is also neutral, like carbon dioxide, all oxidation numbers must still add up to 0. So that means oxygen's oxidation number must stay at -2. Here's another way to think about it. Oxygen only involves 2 electrons in bonds with those of another atom. So the -2 actually comes from the 2 electrons I've highlighted towards the bottom of the triple bond. So this means that dative covalent bonds don't actually influence the oxidation. So let's have a look at another example just to reinforce that. You'll come across the ammonium ion. Obviously, the oxidation numbers this time must add up to +1 because that's the charge. So how does this work? Nitrogen must have an oxidation number of -3 and hydrogen must have an oxidation number of +1. So you can prove it mathematically like that. So that must mean that only the highlighted electrons are actually counted towards nitrogen's oxidation number and not the 2 in the dative covalent bond. Okay, so hopefully this has been a useful extension of oxidation numbers, looking at a couple of tricky examples. Until next time, thanks for listening and see you soon.